Let's do a third symmetry example. Let's answer this question: which of the following orbital overlap integrals must be 0? And we're going to use symmetry to answer this question. Let's look at the px and the pz orbital in the point group symmetry C2v. And what we want is the orbital overlap integrals. And what is that? Well, the orbital overlap integral is the integral over all space of, and what we're going to do here, the px and the pz. So this will be the wave function for the px times the, or complex conjugate, times the wave function of the pz integrated over all space. We're going to use symmetry here, so we're going to find out what the irreducible representation of the px orbital is, and what the irreducible representation of the p. And if these are different irreducible representations, then by symmetry we can say immediately that this integral is equal to 0. And again, we said it's in C2v symmetry. Note that these integrals will be have different representations perhaps if we have different symmetry. So you have to specify the point group before you can answer questions like this. All right, let's take a look. The point group here. All right, here's a point group for C2v, and we're using our crutch here, so we're looking at the x and the z. So the x is b1, irreducible representation, and the z is a1. So a p orbital lying along the x will have the same irreducible representation because there's a plus and minus to the p orbital, as is there to the x-axis. So x is b1 and z is a1. So x is b1, and what do you say, z? So it should be a z, sorry. This is a1. So if we look at the symmetry, so if we just look at the symmetry of these orbitals, px, and we look at the product here, the inner product, pz, that is b1 symmetry times a1 symmetry, and this we know is equal to 0 because b1 and a1 are different irreducible representations of the x and the z. They have different irreducible representations, and so what that means is, since the irreducible representations form an orthonormal set, so they're orthogonal, when you multiply them together you'll get 0. So we know immediately that the overlap integral for the px and the pz is equal to 0. So the answer to the first question must be 0. Yes, this must be 0. Now let's do the same kind of argument using symmetry to show whether px and dxz, whether it has to be 0 or not. We're now looking at the overlap integral of the, px and dxz. So the wave function corresponding to the px times the wave function corresponding to the dxz, does that have to be equal to 0? All right, let's look at the irreducible representation for px. We said that was equal to px, look at the x-axis here, that's b1. How about the irreducible representation for dxz? So this is the d orbital lying in the xz plane. So the irreducible representation of the d orbital lying in the xz plane will be the same as the xz plane. Oh look, xz plane has b1 irreducible representation. So if we take the irreducible representation of the px and multiply that by the irreducible representation of the dxz, that's the same thing as taking the irreducible representation b1 times the irreducible representation b1, and that is not equal to 0. Does the px and dxz orbital, must the overlap integral be 0? The answer here is no, because they have the same symmetry.